Thanks, Helen, and thanks for having me. I know the title is a little bit of a mouthful, so it's
No,
basically
it was
digital
great.
innovation for a greener future. What was that?
It's great.
Yeah. Well, we have to do all these things to be able to. So the overall vision is actually we want to have an impact on our resource management, and we want to enable decision makers to actually make the informed decisions regarding resources management, and that includes critical metals and water, obviously, but also that includes urban geology and our waste management. So we need to characterize the subsurface as we need to do our best effort to do this. And so you might be thinking, why another 3D modeling package is simply because the current packages don't do the job. It's very hard to actually build a model in fully different terrains with the current available packages, whether they're commercial or publicly available. And I will show you in the next few slides how different we are from those packages and why I think we're on the right track, I hope, anyway. Whoops. Yep. So Loop is was initiated by One Geology Consortium, and the CEO at the time was Chris Pygram, also CEO of Geoscience Australia. So the idea actually, or the requirement comes from the geological surveys in Australia, essentially, and then we've increased the group to include the British, the Canadian, and the French geological surveys to some degree, and we also now have USGS as a partner. So the idea, as I said, is to provide a platform to make informed decisions regarding the management of the subsurface. We is a very large team, so I'm not going to name everybody else, but this is all I'm showing here today is not entirely my work or my ideas. We've done a lot of work upstream of the modeling aspect, which is basically trying to capture as much information and knowledge out of the literature. So we do a lot of text mining. We also developed a system to automatically analyze maps and generate geological histories from those maps, and also providing some data, so thicknesses and structural information from the maps. And we've also made a lot of improvement on the geological engine itself and the geophysical inversions. And I'm going to show those, well, at least the geological modeling engine in more details in the next few slides. And the idea, of course, is to be able to map the subsurface and also map it with and characterize the uncertainty within the subsurface and use that uncertainty to actually be clever about understanding the uncertainty related to flow, so water flow or any kind of fluid flow under the ground, or uncertainty on resource estimations and things like this. If you want to know a little bit more, you can go to the loop3d.org website, which is, there is a bunch of presentations like this one today. There are also papers and also link to the GitHub because the software is entirely open source, and we believe and want to adhere to the FAIR principles. At the bottom here, you see all the research and partner organizations. And I think that one of the success of the project so far is the funding organizations and the research organizations are integrated quite seamlessly. So why are we different from any other packages is because instead of interpolating one scalar field to represent stratigraphy, we interpolate 3 scalar fields per geological objects. And so a folding event is an object, and every fault is an object, an intrusion is an object, and faults. Did I say that already? Yes, I did. Unconformity is an object as well. And those 3 rectangular scalar fields are basically defined by the finest strain of each of the objects. So for the folding, we have a directions perpendicular to the actual surface. So this is the actual surface direction for here. We have a directions parallel to the fold axis, and then we have a direction parallel to the extension direction. For faults, we have a directions perpendicular to the faults, a direction parallel to the flow of the fault, and a direction perpendicular to the other 2. And for intrusions, which is through here in the middle there, this is the work of a PhD student. We have a directions parallel to the flow directions, a direction parallel to the growth or the thickness increase of the intrusion, and then a third direction which controls the lateral extent of the intrusions. Because we're interpolating, and then those scalar fields are combined into a 3D models according to the geological history. And I think so the scalar fields are actually allowing us to take into account all the structural elements that a structural geologist will collect in the field, and will allow us to actually characterize all of the objects that we can observe in the field, or from geophysical interpretations, we can actually infer those parameters to build the models. So in terms of the map to loop aspect of the project, so this is the automated analysis of geological maps. It allows us automatically to build a stratigraphic pie, if you want, on the left hand side here. So that's your stratigraphic column, and it's represented as a graph, and each of the relationships are either faulted or conformable or unconformable. And the thickness of the lines, for example, can represent the length of contact between different units on the map. We can also infer the fault network. So this becomes a very complicated graph if you have a lot of faults, but there is also a way to, these faults are classified in terms of the length on the map. So there is an automatic way almost to upscale the fault network. And also you can map out, obviously, the fault formation relationship for this table. You can also extract geometrical information. So these two images here are showing thickness estimations of each of the formations that we can use for the modeling, and also offset, apparent offset along the faults based on the map pattern. So we've developed, we've basically automated the model building from your geological maps and data served by the geological surveys. An example here from the Flinders Ranges, where you have the points represent structural information, so the strike and deep information of bedding. The user just has to draw a rectangle, you press a button, and in about 11 minutes, you get this model for here in the middle here. And we don't even using the structural element at this stage either. But there are limitations. So this is an example from the Hammersley Basin. On the left-hand side is a model. On the right-hand side is the model in color, and the line correspond to the initial map. And you can see that there are some errors, especially along the faults. And the reason for that is all the parameters are not known. So we very rarely know the deep and the shape of the fault. We rarely know the offset and offset direction of faults, or if we do know them, they're actually hidden somewhere in papers and reports. They're not on the maps. So the future of loop is really going to be Bayesian inference on steroids. And what I mean by this is we actually need to do a lot of work on the automatic analysis of maps using Bayesian inference to try to infer those parameters just locally around the geological object we want to characterize. So here is an example in 3D. We have a fault. In this case, the geometry of the fault is known. We know the deep, we know the strike, we know the shape of the fault, and that fault is offsetting two horizons, which are represented by those yellow dots on both sides of the faults. And basically what we're looking for is we're looking for the direction and amplitude of the offset across the fault, and in order to reconcile those two horizons into two continuous layers. And down here on the left-hand side, on the bottom left, you see the joint probability between the pitch of the offset and the amplitude of the offset. So that joint probability basically shows you the posterior distribution of all the models that are actually fitting the likelihood function, which is reconciling those two layers. So that means that we can have many solutions for the same fault and the same map pattern at the surface. But what we can say from this is you can see that the pitch is either negative or positive, and basically that also relates to the deep of the fault. The fault could be dipping to the east or to the west, or north or south here, but let's just use east or west. And what we're proposing is actually using geophysics and geophysical inversions to reduce the parameter space. So with geophysical inversion, we should be able to infer which direction at least the fault is dipping. So let's say to the east only. So that means that this part of the model space, the parameter space, would disappear. So we would provide much more informative priors for the modeling engine. Yeah. Here is another example where we have a fold. The fold has been faulted by a fault. This is very straightforward for here, and we only know that the stretching lineation, so the striations, is horizontal. So it is a structured system, but we don't know the amplitude of the fault. And our likelihood function is actually to reconcile the fold and understand the wavelengths of the folds. So these are again a bit more complicated system with more parameters. We have the coefficient of the Fourier series. We're fitting to the fold data. I didn't go through that. We also have the fold wavelengths and the fold displacements, and basically these are multiple realizations that are acceptable, and that gives us that would give us that would give us priors to be able to model that system. As you can see here, in terms of predicting where we should add more data, these are multiple realization of the fold profile. And you can see that there's a thickness of the line. So there's a number of realizations is so it's more spread as you go away from where we have data. So obviously adding data for here and there would allow us to reduce the uncertainty quite dramatically. And so basically that's what we want to do is the resulting posterior distributions through the modeling stage. We actually want to use that to inform us in terms of where to collect what type of data in the next stage of pre-competitive data acquisition, for example. Lastly, so I go back to my, I think I'm finished. I'm going to go fast here, but I want to really make the link with a greener future. As I said, so if you look at a mine, everything is being automated as we go. The only thing that's not automated is geology. If we want to characterize uncertainty, we need to have automated systems because we need to be able to run multiple scenarios. And really the vision is to help manage our resources, but also reduce the mining footprint. So we want to optimize the drilling. We want to optimize the ore body knowledge so that you can actually better extract the metals with less resources needed. And this will work because because it will work. I think what we've done with Loop, with a structural frame and providing that curvilinear coordinate system throughout the entire volume allows us to do geostatistics very easily as well. So that means that we in the next iteration of Loop, we'll be able to do property modeling within the Loop formulation of the implicit geology, and also propagate that uncertainty through the entire workflow, including resource estimation, flow modeling, and everything else we want to do with our subsurface models. That's it. Thank you very much.